Have you ever stopped and wondered how exactly your computer finds a server halfway across the world in just milliseconds? I mean, it really does feel like magic. But it's all run by this complex, invisible handshake happening constantly all over the globe. So today, we're going to pull back the curtain on the protocol that makes the entire internet tick, and we're going to do it by solving one very, very strange real-world puzzle.
So, check this out. It all starts with this post from a network administrator on Reddit. They were trying to make a pretty standard change to how traffic gets to their network. They did everything by the book, used the right commands, but then nothing happened. Not for a few seconds, not for a few minutes. For 12 straight hours, the internet just seemed to be completely ignoring them. And then, poof, it just started working.
And that, right there, is our mystery. What in the world could cause a 12-hour delay for a routine change on the internet? Was it a bug? Did a router somewhere just give up? Or is there something much, much deeper going on in the internet's plumbing? Well, to figure it out, we've got to first understand how the internet is actually built.
All right, let's get into the core design. To crack this 12-hour mystery, the absolute first thing you have to get is that there isn't one single internet.
That's right. The internet is actually this huge, sprawling collection of thousands of totally independent networks that have all just agreed to talk to each other. So you should think of it less like one big, centrally planned highway system and more like a crazy quilt of city streets, private toll roads, and county lanes all stitched together. And each one of those individual networks has a special name.
They're called autonomous systems, or an AS for short. An AS is basically any network that's run by one organization. Think Comcast or Google or your local university. And each one gets its own unique ID number, called an AS number. These are the Lego bricks that the entire internet is built from. So, the big question is, how do all these separate Lego bricks know how to connect and talk to each other?
And that is where the Border Gateway Protocol, or BGP, comes in. You can honestly just think of BGP as the internet's own GPS. It's the language that all these different autonomous systems use to shout out to their neighbors, hey, I can reach these addresses, and here are the paths I know about. It is literally how a data packet leaving your house in Ohio knows how to get to a server in Tokyo.
Now, BGP actually has two flavors. There's internal BGP, or IBGP, which handles routing inside a single big network. But for our story today, the one we care about is external BGP, or eBGP. This is the version of the protocol that performs that handshake between all the different autonomous systems. It is the thread that stitches the entire global internet together.
So, if the internet is just a bunch of separate networks, how do they decide who to connect to? Well, it's not magic, and it's definitely not automatic. They have to actually form relationships and make deals with each other, both on a technical level and, you guessed it, a financial one.
This whole process is called BGP peering. It's like a formal agreement where two networks set up a direct link between their border routers. Once that connection is live, they start sharing their routing tables, basically telling each other, hey, if you send me traffic for these destinations, I'll make sure it gets there.
And these peering deals are all about business. You know, a small network pays a bigger provider to get its traffic out to the world. Two massive networks, like maybe two big streaming services, might agree to peer for free because it saves them both money. And then you have these places called Internet Exchange Points, or IXPs, which are like these giant digital marketplaces and huge buildings where hundreds of networks can just plug in and easily make deals with each other. And all these decisions directly affect the cost, speed, and latency for every one of us.
Okay, so now we get it. The internet is a web of autonomous systems, all connected through BGP peering deals. So let's get back to our Reddit admin and their 12-hour nightmare. We finally have the tools to understand what they were trying to do, and, more importantly, why their first attempt was a total failure. The first tool they reached for is something called local preference. Their goal was to influence traffic coming into their network from the internet. They wanted to make one of their connections the preferred one, but when they tweaked the local preference, crickets. Nothing happened. So what gives? Okay, so here's the deal with local preference. It's a BGP setting that helps your own network decide which path its outbound traffic should take. Imagine you have two doors leading out of your house to the internet. You use local preference to tell all your own routers, hey everyone, always use door B, it's way better. The door with the highest preference number wins. It's that simple.
And this, right here, is the absolute key to the admin's mistake. The word local and local preference is there for a reason. It's an internal-only setting. It's like writing a note on your own whiteboard that says, use the front door. The rest of the world can't see your whiteboard. They have no idea which door you prefer. So while it's fantastic for controlling how traffic gets out of your network, it does absolutely nothing to influence how the rest of the internet sends traffic into you.
So after realizing that mistake, the admin switched to the right tool for the job, something called AS-Path Prepending. Now, this is one of the classic ways you can influence your inbound traffic. And the idea is actually pretty clever. You deliberately make one of your own paths look worse, less attractive to the outside world. Here's how it works. One of BGP's most important rules for choosing the best route is to pick the one with the shortest AS path, basically the path that crosses the fewest networks. So with AS-Path Prepending, our admin tells their router, hey, when you advertise our network through provider A, the one we don't want to use, add our own AS number to the path a few extra times. This makes that path look artificially long. Now, to the rest of the internet, the path through provider B looks way shorter and more efficient, so they start sending traffic that way. It's basically like telling your GPS to avoid a certain highway by marking it as having a 5-hour traffic jam.
So the admin finally used the right tool. They set up the AS-Path Prepend just right. But that still doesn't explain the 12-hour delay. And the final piece of this puzzle, well, it reveals one of the most fundamental design principles of the internet. It was built to value stability way, way more than speed.
And this is it. This is the big reveal. Unlike the routing protocols inside your own network that can fix a problem in less than a second, BGP is intentionally designed to be slow and careful. Just imagine for a second if one unstable router in Brazil could cause routing tables all over the planet to update every single second. The whole internet would just grind to a halt. So BGP's slowness, it's a feature, not a bug. The specific mechanism that almost certainly caused that 12-hour delay is called route flap damping, or RFD. You can think of it as a penalty box for misbehaving network routes. If a route keeps appearing, disappearing, and changing over and over, what engineers call flapping, BGP routers will start to penalize it. And if it keeps it up, they'll just ignore it entirely for a while to let things calm down. So let's just quickly walk through this graph. See how that jagged line keeps climbing? Every time a route flaps, its penalty score goes up. If it flaps too many times in a short period, that score crosses the suppress limit. At that exact moment, the router just stops telling anyone about that route. It's gone. Then the penalty score starts to slowly decay over time. And only when it drops all the way back down below the reuse limit will the router consider it stable enough to start advertising it again.
Now here's the kicker. It turns out the original default settings for route flap damping were known to be way too aggressive. They would end up punishing totally normal network changes and cause these long, unnecessary outages. It got so bad that the internet engineering community actually published new, much more conservative recommendations that only punish truly problematic routes. But the catch is, not every internet provider out there has actually updated their settings.
And that solves our mystery. When our admin was making all those changes, first trying local preference, then switching to AS-Path Prepending, it's almost certain their upstream provider's router, probably running those old aggressive RFD settings, saw all this activity as instability. It started adding penalties, the route crossed the suppress limit, and bam, the admin's network was thrown in the penalty box. It took 12 long hours for that penalty to finally decay enough for the route to be considered trustworthy again. The delay wasn't a failure. It was the internet protecting itself. Just a little too aggressively.
You know, when you really look at it, the internet's core protocols are a masterclass in trade-offs. BGP chooses global stability over the instant gratification of one network's changes. And this whole story reveals that fundamental tension at the heart of internet engineering. It was built for resilience, to survive faults and chaos. But as we demand more and more speed, more responsiveness, how do we evolve these systems without breaking the very stability that allowed the internet to grow into what it is today? That's the question that network engineers grapple with every single day.